What kind of things does C have? What was that? Pointers? Variables? Functions? So in the beginning of this class, we're talking about functions and methods. And for the beginning of this class, functions and methods are going to be identical. Up until probably week 15, 14, they're going to be identical. And then afterwards, they're going to be identical as well. However, functions and methods are not the same thing. Functions have a very specific definition in computer science. When we talk about them generally, so when you just I can't say the word that's the word. When you generally talk about them, functions and methods are identical. In the strict mathematical sense, they're not. And so for computer science, in the strict sense, functions and methods are not the same. Just remember that. And then if somebody talks about, I'm talking about a function, not a method, you can go like, okay, what the hell's a function again? And we'll talk, and then you'll know. So we'll talk about that later, but for now, functions is fine. What else we got? Pointers, variables, functions. Anything else?
Packages.
When you say packages, what do you mean?
Like importing standard like stdio.
Okay. So that's not exactly a package, but that's I'll call it a package in double quotes because that's a good way to think about it as a package. But it's not exactly a package. We'll talk about what the difference is there. So we're not importing the package; we're including the package, which is slightly different. We'll talk about the difference. Okay. So we haven't talked about structs yet in class, and that's one of the things we're going to cover today. Before we talk about structs, though, let's boil this down. Let's boil these three things, and we'll talk about what that is technically. These three things down into one less thing. So let's only have two things instead of pointers and variable and functions. What do we have?
Loops.
So loops is a control structure. That's correct. But we have that in C, but that's not a function, a variable, or a pointer. It's a control structure, which is good. But let's not worry about that. What are pointers and variables? Very, very short four-letter word. What was that? Data. Pointers and variables are data. What is the value of a pointer? A memory address. An address of another piece of data. That's what a pointer is. What is the value of a piece of data? Well, whatever that piece of data should be. What are the basic data types that we know of? Int, char, long, float, double, short, sure. Is that really all we got? 6 things? 7 things maybe? 8 things maybe? Is that really all we have? The answer is no. We will be able to create bigger pieces of data, and we'll use structs to do it. But we're talking about how we're going to do that. But really, even just a struct is just a piece of data. It's just not a primitive piece of data. We're going to look at the difference between these. What is a function? What is a function? It's a set of operators to perform an operation. So we can call it a set of operators or operations that defines a larger operation. So it's a set of operations that defines a larger operation. And so we want to talk about, if you want to call it an operator, that's okay. Talk about it being an operator. If you want to talk about it as being a set of operations or an operation, that's also a good way to think about it. Because it's not a fundamental operator. When I say a fundamental operator, what am I talking about? Plus or minus, sure. So why are those fundamental operators? Not built into the binary. It's built, what now? What did you say? The CPU? Is that what you said? Oh, C knows how to use them. No. So we could talk about them as being C knows how to use them. Sure, they're the basic operators that C has. Really, it's the fact that the CPU has them built in. Not all CPUs have the same set of operators, however, so we have to combine them in some way. And so usually some C functions that might be built in, for example, subtraction, a CPU doesn't have to implement subtraction. Why doesn't a CPU have to implement subtraction? Subtraction and addition are the same thing, you just add a negative. And so if a CPU doesn't support a subtraction, even though the C function might have x minus 3, really we could say that it's actually x plus negative 3. Those are the same two operations at the higher level. And so the CPU's set of operations is the basic one. And then we can combine those set of operations into a larger operation, which is called a subroutine in assembly language. We call it a function in C. That's where we get this function concept. So we have a higher level operation that is defined by a subset of smaller operations. There's another thing that functions are defined as. Does anyone know what? So this is the one that we want to think about generally. What else are functions defined as? It's already on the board. No. Data. So really, when we say data, all of these things are data. If a language is going to treat a function as data, we call this a first-order language. So a first-order language is a language where functions are data. Or first class, there's also the other term they use is first class. Means functions are data. And this first order, or this first class function is data concept actually builds a number of the things we're going to talk about later. And we have to start thinking about how this idea works in the beginning because we're not able to understand this now. When we start talking about this later, and be like, what the fuck is this nonsense? But essentially, this builds what we call functional programming. This will also build a lot of the power behind some of the languages that we use. If you're familiar with terminologies or technologies like Hadoop, or if you're familiar with terminologies, or if you're familiar with Google as an example, both Google and Hadoop, and these really, when we talk about big data processing, is based upon this concept, that functions are first-order data, or first-class data. And what this means is that instead of just writing a function that takes instead of just writing a function, when we say that we have a function, let's say we have a function foo. If I want to pass a function to foo, I can do that. So here we have the function call, foo. What are the arguments to foo? Foo and 3. So I've written a function foo that takes itself as an argument, and also a piece of data. Now, when you think of this, you're like, why would I ever do that? And this isn't this isn't straight up obvious, and so we're going to start with just knowing that this is possible. Now, the concept behind this is that, what is this thing here? It's a piece of data. What's this thing here? It's a piece of data. And this is our operator that's going to operate on two pieces of data. The fact that functions are operators and data is irrelevant to when we actually pass them. Just that they're doing both things. Java, and this is the biggest detriment to Java, is Java natively does not support this. Java 8 was the first version of Java to allow us to do this. It is the only major programming language that didn't allow us to do this. And one of the results is a number of kinds of programming is exceptionally difficult. Namely GUI programming, or graphical user interface programming, is exceptionally difficult in Java because we cannot do that in Java. With Java 8, we can now do this. However, because we have to be backwards compatible and stuff with other previous versions of Java, it's not widely implemented yet. But the biggest problem with doing things like Android programming is not supporting that until Java 8. Why does Java support this in Java 8? Because Android wanted it. Google wanted it, so Google tried to figure out how to do it. Java 8 supports it. Android programming to do certain tasks, an entire subtype of tasks, which is the graphical portions of it, is almost impossible or very, very difficult when doing this. The other thing that ends up happening is we start seeing, if you've ever seen a Java line that consists of like 14 different concepts in object form or class form, it's primarily because Java doesn't support this conceptual language. This concept of functions as data, completely. Words don't come out of my mouth. So C does support the concept as function as data. However, we do this through function pointers. We're not going to do this a lot in this class, or ever for the most part. But it's good to start thinking about this. So when we talk about C, what kind of stuff does C have? One answer. Data, right? Some of that data happens to be a function or a method that is in a set of operations on other pieces of data. And those other pieces of data are either going to be pointers or a primitive data type or a collection of data types. When I say a collection of data types, I don't mean a collection in the sense of 310 collection. What I mean is a set of data that's going to be set next to each other. And the way we do this in C is, instead of, if I want to combine multiple things together in C, I use something called a struct. Lowercase s instead of capital for this, I guess. I like to think of this as struct is more than one piece of data stuck together. It doesn't matter what kind of data it is, it's just more than one piece of data that's stuck. What does it sound like? Something that we already know. Objects. What are objects? More than one piece of data stuck together, that's correct. Now there's a little bit different thing. There's a little bit different between struct and an object. What's the biggest difference between struct and object? When you say overhead, what do you mean? Yeah, because structs are functions of data. So the biggest difference, and pretty much the only difference between a struct and a piece and an object, is that object-oriented programming languages build the functionality of objects into the language itself, whereas structs do not. If we want object-oriented functionality with structs and to use functions as pieces of data inside of our structs, we have to build that. So if I want to make an object-oriented programming language out of C, I have to figure out how functions work in an object-oriented fashion when I need to build classes. What kinds of things do I need to build that is going to separate a struct from an object? What are the fundamentals of objects that are different than structs? Inheritance. What comes with inheritance? Polymorphism. What else comes with inheritance and polymorphism in classes? Protection. What are those access specifiers? Public, private, protected. Package protected, class protected, whatever those things are. Those are Java things, not real. So, internal. Those things are C#. Anyways, so different languages implement different things. So for example, we say public, private, protected. Those are the three main kinds of access specifiers. In Java, Java also implements a thing called package protected, which doesn't exist in any other language. For example, C# implements a thing called internal or sealed, which doesn't exist in any other kind of programming language. C++ doesn't, I think, implement anything other than those three. They might implement something that I'm not thinking of right now. But for the most part, those are only the three that we really care about. And some of those things, like inheritance and polymorphism, we can fake with structs. things like access specifiers, we cannot do in C, ever. It's not possible. And that's because of the way that C is built. So let's take a look at some structs. We'll take a look at the difference between a struct and a pointer and a struct with some data in it. Does anyone know the basic format of a struct? Do you know the basic format of a struct? Is that a right one? Give it a shot. Uh-huh. Excellent. Okay. Curly braces. Some more curly braces. And one last thing. What do you think comes after the last curly brace? Semicolon. Right? So this is the reason why we have a semicolon on the end here is because the semicolon is usually we think of structs as being a single line, and the semicolon is ending that struct. What I put inside of here are all of the members of that struct, and all of these members are going to always be public, and this is where we can't get access specifiers. Anything I put inside of a struct is always going to be public all the time. As an example, let me go ahead and put two integers in. Let me put an integer and a float. So if I put an int x and a float pi inside of here, that means that I now have the two different pieces of data stuck together inside of this struct. And the name of this struct is struct name. So let's give it a different name because name isn't very helpful for us to understand what this means. Somebody give me a name. Monkey? We do this all class. Okay. So we have the struct monkey. Inside of that monkey, we have the integer x and the float pi. This piece, when I mean it's stuck together, what does that mean? It's true. Monkeys have x and pi. Not we don't say monkey. We say struct monkey. Struct monkeys have x and pi. That's correct. Well, what else do I mean when they say they're stuck together? Correct. That's true. And yes, and so they are in the same scope. And anywhere I define, one of the things is anywhere that I define a struct monkey, I'll always be able to access the x the same way I'll be able to access the pi. That is true. That is good. What else? Contiguous in memory. So this is the really big thing about being stuck together. When I say they're stuck together, I mean that they're contiguous in memory. So if I draw my memory box here, and I'm going to draw a monkey. Let's suppose that our code is up here. This is our code. And I dynamically allocate a single monkey. That single monkey will take up all of that memory. Why did I draw it that way? Sorry? It is in the heap, you're right, because I dynamically allocated it. How would I dynamically allocate that? How do we dynamically allocate memory? Starts with an M? Malloc, right? So we're doing memory allocation, malloc. Why did I draw it like this, though? You're right, why did I draw it with 8 bytes? Because of an int and a float. How big is an int? 4 bytes. How big is that float? 4 bytes. Which of these two things is the integer? It's the first one. This is the integer. Why is this one the integer? This is the first one I declared, and the second one is going to be the float. They're going to be stuck together. If I allocate 2 monkeys, 2 struct monkeys, how many bytes do I allocate?
16.
And 16, how do we know it's 16? Because it's times 2. So we know we get that one, and then we also get the second one here. This first row will be the integer because it's the first one defined. What's the second row going to be?
Float.
And this one's going to be,
Integer.
and that's going to be
Float.
float. So it's going to go int float in memory. That's the way that's going to be defined. Do I want to have to think about the fact that it's going to be int float in memory? Do I want to have to think about it? No. And the answer is I don't have to, which is good. So when we define some things, let's go define some struct monkeys here. So if I have a line of code that looks like this, let's say I have my int main up here, so my main starts at the top. If I have a struct monkey, give me another variable.
Banana.
Banana. Put this in your color so it's obvious which part is what. And spell banana?
Yes.
Yes. All right. So I have my struct monkey banana. My banana is going to be declared or going to be allocated where? It's either going to be declared on the heap, it's either going to be allocated on the heap or on the stack. Did I use malloc? Where is it going to be declared? Stack. So if I did not use malloc, it gets declared on the stack. What happens when this function finishes? That memory goes away, right? Let me go and declare another one that's going to be allocated on the heap instead of the stack. So we'll do another struct monkey. I need another variable name. Huh? Chimp. How do I make this chimp such this monkeys so that struct monkeys will be declared on the heap, not on the stack? What special thing do I need to add? $sign is bash. We're not in bash.
Asterisk.
An asterisk. What's the asterisk going to do for me? It's going to make it a pointer. So the variable chimp is going to be declared on the stack, right? But I'm going to then allocate some memory down here that my pointer will point at. So chimp is not technically a struct monkey. Chimp, the variable, is a struct monkey pointer, right? So that chimp points at some struct monkeys. Okay. Let's go ahead and allocate some space for us. So we'll say chimp equals.
Use a different color.
Equals. How do I allocate memory on the heap? Malloc. We'll get to how big we want to do it here in a second. So I'm going to make this a really big parentheses because we're going to go through a couple iterations. Let's say I want to allocate 2 struct monkeys. How many bytes do I have to allocate? 16 for my 2 struct monkeys. Like so. And what's this thing? What am I going to put in the front here? I'm going to cast it to a struct monkey pointer. It's a struct monkey. That's not how you spell monkey. So our chimp is being defined, is being set to the struct monkey pointer that gets returned from malloc. That's going to be 16 bytes. What happens if I define that to be 12 bytes? What if I only said 12 here? What happens? I lose 4 bytes. Does chimp know of the fact that I lost 4 bytes?
Nope.
No, why not? Well, it doesn't care. It just points in the beginning. Does chimp know how big it is? No, unfortunately it doesn't. So if I allocated 12 bytes, let's go look at a couple of usages, and we'll see how to fix all this problem. Because one of the things that's going to happen is sometimes our structs are going to be big and complex, and we're not going to know what we want really. So we have our chimp. Let's go ahead and allocate. Let's go ahead and set these 4 values, or try to set those 4 values. If I want to set the first x of chimp, the way I'm going to do this is the same way that we did with a array. So I'm going to say chimp array access. What's the first one? 0. Dot. The dot is going to say go into the structure. Which one do I want? X equals. Let's give me a value. Let's say 3. What that's going to do is that's going to say, let's take the first chimp, which are these 8 bytes, find the x, which are these 4 bytes, and set it to the value of 3, which is going to be this, 0, 0, 0, 0, 0, 0, 0, 3. Any questions about that? Yes? Okay. So chimp is a struct monkey. Struct monkeys know they are how big? 8 bytes. So when I say, let's go and access the x for the second chimp. When I want to access the x for the second chimp, I say chimp of 1. When I say chimp of 1, how many bytes should I skip? 8 bytes, because I know that struct monkeys are 8 bytes. It doesn't know how many bytes are allocated. That's the difference. Cool? So this is a good point. We're gonna look at this guy here. So the chimp of 1 there, dot, and then x equals, let's say, 4. That'll allocate the second guy down here to 4. Like so. How do I get the first guy's y? And how do I set it to pi? So I'll say chimp of 0, because that's the first guy. Dot y, and then I can set it to, say, for example, 3.14. I'm going to write the f there. That means it's a float. If I don't write the f, it defaults to a... So it's a double. So if I don't write the f, it defaults to a double. And so if you get compiler errors that say, hey, double float, not the same thing, you either want to put the f on there or get rid of the f, one of those two things. That's going to write that 3.14 here. I have no idea what the hex value looks like. I think it's this. 0, 0. No idea. No idea. 3.14. I can't do IEEE 7, whatever it is in my head. So. Let's go and set the second chimp to 2 pi. So we do the same thing. We would say chimp of 1 dot y equals 6.28 f. And it'll go in, and what's it going to do? What's going to happen here? Huh? Y pi? Oh, I'm sorry. It's supposed to be pi. I'm sorry. You're right. My bad. That would error. Pi. You're correct. So we have 2 pi for the second pi.
It's going to write 2 bytes of float inside of the structure. That's going to write 2 bytes of garbage.
So when we say, well, okay, you're close. When we say 12, how many, that's the first 3 rows here. Is this row valid at all? Right? This row is not valid. When I try to do this right, because I only said 12 there, this is going to fail, and my program will crash. If I'm lucky, this right will succeed. But then later, when I try to access it, I have no idea if that value is still valid. It might be garbage, it might be something else. So one of those things is, really, if this right succeeds, I'm not lucky. I'm actually unlucky, because my program should have crashed at this point. If I'm unlucky enough for my right to succeed, when I read that value back, I don't know what it's going to be. Because this malloc is too small. Now, I don't have to worry about the size. I don't have to worry about how big each one of these bytes is when I write to it here, because this chimp variable is a struct monkey, which knows that it's 8 bytes. So when I go from chimp of 0 to chimp of 1, it knows to skip 8 bytes. If I said chimp of 2, it would skip 16 bytes. If I said chimp of 3, it would skip 24 bytes, and then 32 bytes. So it should skip that many bytes each time. The size of a struct monkey. doesn't know if it's going to write off the end of memory. And if it tries to write off the end of memory, your program is going to crash. And we don't know that. Who's responsible for making sure it doesn't write off the end of memory? We are. The programmer is. Yes? So when I said malloc 12 here, what I did is I allocated 12 bytes of memory. So I didn't allocate 2 chimps. I just allocated 2 bytes, or 12 bytes. Then when I set it to the chimp location, I'm saying that I have 2 chimps. I fucked up and I only have 1.5 chimps, right? And so I don't. And so there isn't a way for us to know that this data is a chimp unless we take a pointer that points to it as a chimp. Does that make sense? So we don't know that at all. When I say chimp of 0, I'm saying the location of chimp plus 0 bytes. When I say chimp of 1, I'm saying location of chimp plus 8 bytes, regardless of what is here. I don't know what is there. We'll do this some more. Well, there are no strings in C. There are only characters.
It's essentially an array.
Correct. It's just an array of characters. This is an array of chimps in this case. If I have enough memory allocated or not, I don't know, is the answer. So let's look at how I can allocate the right amount of memory here. Fortunately, C does give us this thing, which is called size of, and so I can say size of. And I can say, inside the size of, I can say struct chimp. The size of the struct chimp. And how many struct chimps do I want in this case? 2. Struct monkey, sorry. Chimp is the variable. Thank you. So I get 2 struct monkeys. That's what happens when variable names are. What happens when names are similar? You get screwed up in the brain. Struct monkeys and struct chimps. So the size of the struct monkey, we know is 8. And I get 2 of them. What this allows us to do is now, instead of specifically writing 12 or 16 bytes in there, if I come in here and I say char C, and I add a char C in there for the character, now that size is no longer 16, now it's 17 bytes. Where the fuck do I put it? How do I make sure that I'm allocating the right amount of space and all this other garbage? So what this is going to do is this is going to verify for me that this will automatically give me the correct location. The other thing that this will give me is it will also put it correctly on bus boundaries. If you remember or are familiar with bus boundaries from 237, it will automatically over-allocate memory if it needs to over-allocate. So, for example, it might not be possible for me to allocate memory like this. I might have to allocate 2 characters or 4 characters instead of a single character. And the size of and the struct and all of this stuff will automatically do that for me. But this is the reason why we want to do this format. Yes? No. Yeah. Okay. So I'm going to get rid of that char C on there. That was just another demonstration. So let's talk about what it means to have this line like so. I'm going to erase this real quick. Just remember our struct monkey declaration. Let's take a look at what this chimp of 0.x is. And can we do it a different way? And the answer is yes, absolutely we can. Because this is C, and C lets us do stuff like this. Let's go ahead and say we're going to declare an integer pointer. So we'll say int, we'll declare a pointer another variable name? You have another monkey thing? Cheese? Yes. Cheese. This is going to be cheese. It's not a monkey thing here. I'm imagining monkeys You think you have spelling problems. All right. So we have this integer pointer star cheese. So we have this variable cheese, which is an integer pointer. And what we're going to do is we're going to say cheese equals the integer star of chimp. What did I do there? So cheese is a pointer, chimp is a pointer. Cheese and chimp now both point at the exact same thing. Let's suppose this memory address down here, let's give it an address of 00003204. Let's say that's the memory address of that location. So 3204 is that memory location. I'm going to go ahead and write the value of cheese over here. So cheese has a value. And chimp also has a value. The value of chimp is 3204 because that's what the mallet gave us. What is the value of cheese now after this assignment? 3204. It's the same. So if these point at the same thing, what is different between cheese and chimp? Cheese is an integer pointer. Chimp is a monkey, struct monkey pointer. If I say we do 2% d. So that's percent d, comma percent d. So 2 integers. And I say cheese of 0. And I say chimp of 0 dot x. Take a look at that. So, yes. We're going to talk about that in the next one. So, cheese of 0 refers to 3204, the first guy, which is the value of 3. Chimp of 0.x is 320.4x, which is that 3. So this is going to print 3 and 3 both times. Now if I say, let's go ahead and change this from cheese of 0 and chimp of 0 to cheese of 1 and chimp.pi. When I say cheese of 1, what do I mean? So when I say cheese of 1, so conceptually, at the higher level abstraction is, I want the second integer in my array of integers. So when I say cheese, when I'm referring to the cheese variable, I'm referring to all of this memory down this way as an integer. Every 4 bytes in this array, because all this is just an array, every 4 bytes of this array is going to be treated as a single integer. So when I say cheese of 1, I'm talking about the second integer. The second integer is this one right here. What is that value as an integer? The answer is I don't know right now. We can actually figure this out. We'll program this up and see what it actually prints out. This integer right here is not 3.14. It's some float value as an integer. It might be 3. I don't know if it'll print 3 or not. It might be able to figure out that that's a float convertible. But it probably won't. It'll probably be some, what we consider to be garbage value. Whereas chimp of 0 of pi says that this is a float, I'm going to want to then print that as an integer with a %d, and that's going to truncate that 3 to that 3. So instead of being 3.14 for this one here, the second one will be 3.14. What I expect out of this should be 3, and this one should be garbage. Because essentially, I'm saying take this bit pattern that means this 3.14 as a float, don't think of it as a float anymore, treat that same bit pattern as an integer. And so, for example, if the float says that the integer, the bit pattern should be 00110101101, that's not the value of 3 as an integer. That's the value of something else. If I then change, so we'll try this a couple times on the overhead in a minute. So use of 2 and chimp of 1.x. Those two values are going to be what? Which 4? The same 4. It's this same one down here. So when we say cheese of 2, we're saying take the pointer of cheese. This translates to take the value of cheese, 3204, add into that 3204. How much do I add to it? 8. How do I know the value is 8? It's the size of an integer times that value 2. And so this is going to be 3204 of 4 times 2, which gives me 8. When I say chimp of 1, this says take the chimp 3204, add in the size of a struct monkey. How big is the struct monkey?
8.
Size of struct monkey, which is 8, times how many? 1, which gives me 8 times 1. To get to the same exact value. We don't know if that memory is valid. We don't know if we can write to it. We don't know if we can read it. We don't know anything about that memory. The only way we can assume that that memory is valid is if we have previously mallocked it for us. If we have not previously mallocked it for ourselves, we cannot access it. Who's responsible for making sure that we don't go off the end? We are. Who's responsible for making sure we reallocate the right amount of space? We are. Who's responsible for doing all those things? Us. This is what C does. This is how C works. Java gives you a lot of other things for free. Java does the allocation for free, does the memory management for free, does the pointers for free. You don't have to do any of this. This is the reason, one of the reasons why people like to program in Java. One of the reasons why people like to program in C is I get much more control over things. If I wanted to treat this guy as an integer instead of a float, I absolutely can. What do you mean by create a struct monkey?
Like after we use the struct, we have to create a struct.
Ah. So if I want to not have a memory leak, I then, after I'm done using my struct monkey, I have to free it. Correct. Other questions? Yes. I free the chimp. So what I would do is I would say free chimp, and then the chimp would be free. All that, if I free the chimp, then all the struct monkeys in that chimp are gone. Other questions? What has this all done for us? What are the pointers? Why does this matter? This all matters Because when we talk about Java allocating memory and Java memory management freeing memory, this is what Java is doing for us. When we talk about Python, doing automatic memory management, automatically freeing and saving and restoring and allocating memory, this is what it's doing for us. When you talk about a language that does automatic memory management, these are the things that it does. If you want to talk about the fourth element of an array, the fourth element of an array means the size of however big it is in bytes times the number of things that you want, which gives us the number of bytes to skip. That's how we always do these processes. Knowing these things will give you better insight into how, if a program is not running as you expect, you can then break the abstraction layer a little bit and think about why is that not working the way you expect it to. Go ahead and do this sample so we can see what actually happens. All right. And if we have time, we'll talk about files a little bit. But all right, so we're going to do a pound include stdio.h. I'm going to do my struct definition, so we'll have our struct monkey here. We'll have our curly braces, we'll have our int x and our float pi, and our curly braces and our semicolon. Do an int main, like so. I don't need to take any command line arguments, so I don't have any command line arguments, but I will return the 0. I totally screwed that up. Let me do it all again. Actually, if you're not familiar with PuTTY, if you highlight all that stuff there, that copied it. Now if I right click, it pastes it. So that's better. All right, so now what I'm going to do is I'm going to say struct monkey star chimp. And so chimp equals pointer, or the, what's this called? Typecast struct monkey star to malloc of size of struct monkey times 2. I'm also going to declare my integer pointer up here, so int pointer, what was it, cheese? And then cheese is going to equal integer pointer of chimp. Like so. And I can go and say chimp of 0 dot x equals 3. Chimp of 1 dot x equals 4. Chimp of 0 dot pi equals 3.14. And chimp of 1 dot pi equals 6.2. So, any questions about that part? This one? Anything else? Yes.
Is it valid to do chimp
Sure. Absolutely. You could just say 2 times. Okay. All right. So what I'm going to do is I'm going to say printf. We'll do a number of these printf lines. This is going to be %d. %d. Well, let's do %d. %d with the new line. This is going to be chimp of 0, comma cheese 0. Chimp of 0, let's do cheese first. We have cheese first. We'll do cheese first. Chimp of 0 dot x. This is going to be cheese of 1 and chimp of 0 dot pi, like so. Let's go and compile this. ECC test.c out there. Now I run a dot out, and you can see that we get this. Let's try %f on the chimp one, see if that %f will make it print out correctly. I was not expecting, I was expecting it to be. Let's see, maybe I screwed something up. But if we look, not exactly what I was expecting, but if we look, this value here and this value here are not the same because of the way that we're interpreting those two values. If we let's see what happens when we typecast this to an integer first. Let's see what happens there. There we go. So there's that 3 that I was expecting. So that was the float and the value coming out faster and stuff. Let's go and take a look at the next value. So this is going to be cheese of 2 and chimp of 1 dot x. We'll run it and you can see there's the float. Questions about this? These are pointers. This is how we do pointer math over here. We're talking about pointer math. We can also talk about doing pointer math with a slightly different notation. So for example, if I want to do the exact same thing, so let me go and do this chimp of 0. Let's go and reassign it. Let's do it a different way. Let's say, do this one. Let's say, do this with multiple parentheses. Chimp plus 0 dot x equals, let's say 7 in this case here. Let's go ahead and figure out what that line reads as. Here I say chimp, the value of chimp plus 0. What do we think we are doing here? So we're not accessing the first chimp here. Well, we're going to be. But what are we doing with just the chimp and the plus 0? So 0 is not a pointer. 0 is just a number. But we are adding the pointer chimp to something, right? So what we're doing is we're going to be offsetting, because that's the technical. But really what we're doing is we're just adding some number to chimp. So for example, if chimp is 3204 and we add 0 to it, what are we going to get? 3204. When I do the star after that addition, that star says access that memory location. And then the dot x says let me get the x portion of that memory location. So no, it's not commutative like that. Is that the right word? I don't know if that's the right word. Not distributive? Yeah, it's not distributive like that. Thank you. Correct. So for example, let's go and compile this and run it. And when we compile and run this, we said chimp of 0.x equals 3, and here we're assuming that chimp of 0.x is going to become 7. So we expect it to print 7 for both of them. Let's verify that's actually what happens. We can see that we have the 7 and the 7 and we've got a form of x's, which is correct. Let's go ahead and take another look. Let's go and try that again with a different value. Let's use a different offset. So what offset do you think we should use right here instead of 0? 3? Why do you say 3? I don't know. It's good. You're making up numbers. Let's see what happens. I like it. All right. Work? Well,
We changed something else, alright?
we changed something else though, that's for sure. We actually got lucky that it didn't crash. I'm going to tell you that right now. What do you think we should try to print? Which cheese of what should we try to print here?
Okay.
There you go. Cheese of what?
3 in this case.
3. Why do you say 3?
Because we added 3.
So because we added 3 to chimp, right? Alright, so let's see. Cheese of 3, because cheese is the integer one. Let's see if it'll print out correctly. Did that give me 7 down there? No, that gave me some sort of garbage. Good guess though. So what's wrong with that? Why is cheese of 3 wrong when chimp plus 3 is wrong? Or different? When I say chimp plus 3, what am I saying? I'm saying the pointer plus 3. 3 what? Ah, that's a question. That's an excellent question. If I'm saying 3 bytes, that might be what I'm saying. So let's figure out. So chimp plus 3 bytes. And then down here, when I say cheese of 3, I'm saying cheese plus how many bytes? The size of cheese. How big is an integer?
4 bytes.
4 times, which would be
12.
12. So should that print the same thing if that's 3 bytes? No, right? How do we make those two things print the same thing if it's 12 bytes? If cheese is 3 is 12 bytes. Change this to 12, right? Let's go and change that to 12, see what happens. This might actually crash it. Let's see what happens. Didn't crash it. Is that 7? No, it's not. So what's happening? What's the other option? Because we know for certain, with great certainty, that cheese of 3 means that 3204 plus 12. I know that. If this does not set 3204 plus 12 to 7, what is this doing? 12. What does that 12 mean?
That's pointing at something else.
Adding 12 what?
Bytes.
Not bytes, because we know that this is chimp plus 12 bytes. Right here. Huh? It's not, so not 12 chimps, it's 12 struck monkeys, you're right. So we're adding 12 struck monkeys here. So the compiler is smart enough to say, hey, you had a struck monkey here and you added 12, you probably want to add 12 struck monkeys. Is what you want to do. That's what it's saying. So how do I do it? So let's make this 12 instead of changing that 12. Let's change that 3 such that we print that 7. So that's 12. 12 times 8 is 96, right? So that should be 96, right? I'd put 96 there. 96 divided by 4 is. Ah. Google save me. 24. Holy crap, there's the 7. Okay. So these are the ways that we can add the different parts together. So when we say chimp of 0, we're saying chimp plus 0. When I say chimp of 1, I'm saying chimp plus 8 bytes. When I'm saying chimp plus 12, I'm saying add 12 chimps, which is 12 times 8, which is 96 bytes. I'm going to write some funky stuff. I'll change this back to a 3 here. Right there. This is what I'm going to do. I'm going to say as char. Oh boy. Let me figure out what it is. There's a struct. Struct monkey. Okay. The hell did I just do? So what I did is I said, let's take that pointer chimp, 3204. Let's say that pointer chimp is no longer a pointer to chimps or monkeys. It now points at characters. How big is a character? 1 byte at a time. So when I say that pointer plus 12, I'm saying add how 12 whats? Bytes. So I add 12 bytes because I'm adding 12 characters. So 30204 plus 12 bytes gives me 3210. 16. 32010. 16? No. 320C. No, 16. 3210. Yeah. 3210. Give me a crazy good. This is 3210. If you don't know why it's 3210, this is not, that's hexadecimal. 3204 is hexadecimal. 12 more in base 10 gives me 3210 in hexadecimal. So it's okay. You know. And then I was saying, let's take that pointer that was pointing at bytes and turn it back into a struct monkey for myself. And then I'm accessing that struct monkey that was a character. So it was a struct monkey, I turned it into a character array. I moved it, I turned it back into a struct monkey. I'm going to access it now. And I'm going to set that value to 7. That's what I'm doing. A little weird. I understand that's a little strange. That didn't work. Should have worked. T's of 3 should be 12. Should be 7. I don't know where it is. Let's figure it out where it is. So what I'm going to do is I'm going to write a quick test to figure out where it is, because I don't know exactly. Get rid of this guy real quick. 4. I can't put it over there. C, so I'm going to say int I up here. 4I equals 0. 0I is less than, let's say, 10 I plus plus. I'm going to print this for each one of those i's. Got cheese on I for each one. Also print chip on I. Let's go make this 30. Sevens in there? Why not? Why not? So it's possible that it didn't line up. That's probably what I'm thinking is happening here. When I added that 12, that should have lined up, so it should have been okay. But 3, 4, 16. A lot of garbage there. I don't know all those things are. I don't know where the 7 went. Show up where I expected it to. Let's try it again with an actual character pointer though this time. We can do this. We're then going to say if I say 2 and 12 equals 7, somewhere. Alright. I don't know where it is. It didn't happen the way I expected it to. I'll try to figure out why it didn't happen the way I expected it to. I expected it to set one of those values to 7. It didn't let me, or I fucked up somewhere. It's more like whose fault is it when the program fails? So it's my fault that didn't